Ever feel like everyone's suddenly speaking a different language when they talk about AI and machine learning?
It can definitely feel like that, yeah.
But don't worry, we're going to break it all down for you today. Think of this as your crash course on AI and ML without the headache.
We're going deep, but we'll make sure you can follow along. We're talking about what these terms actually mean, how these systems work, and, how they've evolved over time.
Right, because it didn't just appear out of nowhere. And we're coming at this from a few different angles. We've got some amazing material to work with. A lecture from MIT OpenCourseWare that's the gold standard.
Absolutely.
We've also got a super clear intro from Google Cloud Tech, the folks who are really working on this stuff every day.
Yeah, they're on the front lines.
And to round it out, we've got a guide to the fundamentals, which is always helpful.
It's like having all the best teachers in one room.
Exactly. And our mission today is to distill all of that down for you. We're talking key insights, those aha moments, and a solid understanding you can walk away with.
No jargon overload, we promise.
Yeah. So let's start at the beginning. What even is artificial intelligence?
Right to the heart of it.
Well, we found a definition that really clicked for us. It came from a brainstorming session with Professor Winston at Lincoln Laboratory, no less.
Those guys know their stuff.
They described AI as the attempt to make technology think and process information the way humans do.
It's a powerful idea. And what's interesting is that while algorithms are a big part of it, and we hear a lot about those, a full AI system is so much bigger than that.
Right. It's not just algorithms.
It also involves things like conditioning your data, having the right kind of computing power, making sure the AI is robust and reliable, and thinking about the interaction between humans and these AI systems.
Which brings us to something they call the canonical architecture of an AI system.
Yeah, a fancy way of saying how it's all put together.
Exactly. It's like a flow. You start with data, feed that into algorithms, and we'll see there's a whole universe beyond neural networks, and those algorithms process the data to produce knowledge.
And that knowledge then usually gets fed back to a person or applied to a problem. That's where the human element comes in.
The human-machine teaming part, right?
Exactly. And the whole point of that is to gain insights, to understand something, to make a decision, to achieve the goal of the AI system.
And underpinning all of this are those modern computing technologies we were talking about.
It's the engine that makes it all possible. And of course, all of this needs to be built on a foundation of what they call robust AI.
Right. It's not just about making it work, it's about making it work well and responsibly.
Exactly. So that includes things like being able to explain why the AI makes certain decisions, having ways to measure its performance, making sure it's actually doing what it's supposed to, keeping it secure from attacks, and considering ethical implications.
So that's a broad overview of what AI is.
Yeah.
But how did we get here? How has AI developed over time?
Well, the MIT lecture broke it down into 3 distinct waves of development, which is a really helpful way to look at it.
And the first wave was all about expert systems, sometimes called the reasoning wave.
Yeah, this was back in the early days. And the idea was to basically encode human expertise into software, like having an expert sit down and write out a whole bunch of rules. If this, then that.
Like a super detailed flowchart.
Exactly. And it was good at reasoning because it was based on human logic that had been programmed in.
And they gave some good examples, like tax software. It follows a set of rules created by, well, tax experts.
Makes sense.
And even early self-driving cars used expert systems.
Really?
Yeah, to determine the car's different states and how it could transition between them, like driving, stopping, turning, all based on expert knowledge.
So even though it seems kind of old school now, it's still a valid approach.
It is, especially if you don't have a ton of data or a lot of computing power, or if you really need to be able to explain why the system made a particular decision.
Right, because you can just point to the rules it followed.
Okay, so that's the first wave. Then things started to shift with the second wave, called the learning wave, or statistical learning.
Yeah, this is where things get interesting. As we started getting more and more data, the focus shifted to using that data to let the systems learn patterns on their own, rather than explicitly programming in all the knowledge.
So instead of telling a car, if you see a red light, then stop, you'd feed it a ton of data about driving, showing it red lights and braking instances, and it would learn that relationship itself.
Exactly. Like they talked about speech processing. Instead of having super specific rules for every sound, you might use a statistical model Think of it like a general template for how speech sounds work, and then train it on a bunch of speech data so it can learn the specifics.
Right, so the system is figuring out the rules from the data.
Yeah, and they gave the example of self-driving cars again. You might still have those high-level states, but the algorithm would learn when to switch between them based on the data it sees.
So this wave saw big improvements in perception and learning, but the ability to really understand the why behind things, to abstract and reason like humans, was still somewhat limited.
That's a key point. And it brings us to the third wave, which is all about context. They called it contextual learning or contextual adaptation.
Okay, this is where it gets really cool.
Yeah, this is where AI starts to add in context and be able to abstract and reason more flexibly, kind of like how we do.
Like knowing that a chair is still a chair, even if it's upside down or in a different room.
Exactly. It's about understanding the bigger picture, the situation. But here's the thing. The MIT lecture suggested that a lot of what we see today as AI, even if it uses some learning techniques, is probably still in the later stages of that second learning wave.
So we're not quite there yet with true contextual learning.
Not fully. True contextual learning, where the system really understands and uses context like we do, is still mostly in the research phase.
Got it. So where do we go from there? What's next?
Well, they talked about a potential fourth wave, which they called abstraction.
Even more advanced.
Yeah. This would be about an AI system being able to take what it's learned and apply it to completely different domains. Like understanding the concept of a table, not just as a physical object with legs and a flat surface, but as a more abstract idea of a surface for putting things on, and being able to apply that understanding in totally new situations.
That's pretty mind-blowing.
It is. But it's still very much in the future, very early stages.
So we've got these waves of AI development. It's a journey, not a destination. And it's not like one approach is always better than another.
Right. It's about choosing the right tool for the job.
And to help with that, they talked about 3 dials that influence how you approach building an AI.
3 key factors, yeah.
The amount of computing power you have, the amount of data available, especially labeled data, which we'll get into, and your ability to build in knowledge directly.
So if you've got limited computing power and data, but a lot of expert knowledge, an expert system might be the way to go. But if you've got tons of data and computing power, but less explicit knowledge to program in, neural networks might be a better choice.
It's about finding the right balance.
Exactly. And statistical methods often sit somewhere in between, where you build in some general assumptions, but then let the system learn the specifics from the data.
Okay, so we've got a sense of what AI is and how it's evolved. Now let's break down the key components of an AI system according to our MIT source.
Let's get under the hood.
The first component they highlighted is data conditioning. What's that all about?
This is where it all starts. And it's often a much bigger job than people realize. It's about taking raw data, which could be structured data like readings from sensors or logs, or unstructured data like text or social media posts, and getting it into a format that the AI can actually use.
So it's not just a matter of plugging in a hard drive.
Not at all. You need to think about where to store the data, how to organize it, how to index it so you can find what you need. And for unstructured data, you need to structure it somehow. They even talked about using domain-specific languages, think of them as specialized coding languages for different fields to help with this conversion. This step can take a lot of time and effort.
Raw data can be messy.
It definitely can be.
And then we move on to data curation.
Okay, so now that you've got your data somewhat organized, this is where you really start to dig in, clean it up, and prepare it. You might use some unsupervised learning techniques, we'll talk more about those later, to reduce the complexity of the data, group similar data points together, or find outliers, those unusual data points that might be errors.
You're essentially making the data more useful.
Exactly. And a really crucial part of this, especially for supervised learning, is data labeling.
Right, because in supervised learning, the system needs to know what it's looking at.
Exactly. So this is where you add tags or categories to the data. You're carefully checking for errors, identifying any biases in how the data was collected, and highlighting the specific parts that you want the algorithms to learn from.
It's like teaching the system what's important.
It is. And one thing they pointed out is the sheer volume difference between unstructured and structured data. They estimated that something like 90% of available data is unstructured.
Wow, that's a lot of untapped potential.
Yeah, it is. Structured data, which is easier to work with, might only be about 10%, but that's often where a lot of the early analysis and value comes from.
Okay, so we've got our data all prepped and ready to go. Now it's time for the algorithms.
The brains of the operation.
And our source made a point of saying that there's a whole lot more out there than just neural networks.
Oh yeah, there's a whole toolbox of algorithms to choose from. To illustrate this, they brought up Pedro Domingos's idea of the 5 tribes of machine learning.
5 tribes.
Yeah, it's a cool way to think about the different approaches. You've got the symbolists, which include our old friends, the expert systems. Then there are the Bayesians using algorithms like naive Bayes, the analogizers, which are things like support vector machines. They try to find the best way to separate data into different groups. And then, of course, the connectionists, where neural networks live.
So those are 4. What's the 5th tribe?
Oh, right, the evolutionaries. These are things like genetic programming, which takes inspiration from, you guessed it, evolution and natural selection.
So it's not just neural networks running the show.
Not at all. And to help visualize this, they used a Venn diagram. You've got AI as the biggest circle, then machine learning inside that, the neural networks inside that, and finally, deep learning as the smallest circle, a subset of neural networks.
So deep learning is just one part of the whole AI and ML landscape.
Precisely. And like we talked about earlier with those dials, the choice of which algorithm to use really depends on your specific situation. How much computing power you have, how much data, and how much knowledge you can build in.
No one-size-fits-all solution.
Nope.
Okay, the next key component is modern computing engines. We all hear about CPUs and GPUs, but what else is in the mix?
Well, CPUs and GPUs are still the workhorses, but things are changing. As Moore's law has slowed down, that's the idea that computing power doubles every couple of years. We're seeing the rise of specialized hardware designed specifically for AI tasks.
Like custom chips.
Exactly. Google's TPU is a good example. And Lincoln Laboratory is working on things like graph processors, which are good for certain types of AI calculations.
What about things like neuromorphic computing and quantum computing? Those sound futuristic.
They do. Neuromorphic computing is inspired by how the brain works. It often uses systems that don't rely on a traditional clock signal, so it's very different. It's still mostly in the research phase, though. And quantum computing, while it's showing promise in areas like solving complex equations, it's not quite clear yet how it will be applied to AI.
So for now, it's still mostly CPUs, GPUs, and some of these specialized chips.
For the most part, yeah. And importantly, a lot of these are commercially available, so people can actually start using them.
Okay, so we've got the data, the algorithms, and the computing power. Now let's circle back to robust AI.
Right, because it's not just about making AI work, it's about making it work safely and responsibly.
And they talked about a sliding scale of human involvement, depending on the consequences of a decision and how confident we are in the AI.
Right, so for high-stakes situations where we don't fully trust the AI, you want a human in the loop. But for less critical tasks where the AI is really reliable, more automation is okay.
So it's not all or nothing.
Nope. And within robust AI, there are several key areas. Explainable AI, being able to understand why an AI made a decision. Metrics, having ways to measure how well it's performing. Verification and validation, making sure it's doing what it's supposed to. Security, protecting it from attacks, including things like counter AI, which is AI designed to attack other AI. And then, of course, the ethical and societal implications.
There's a lot to consider.
It is. But it's essential if we want to build trust in these systems.
And the final component in their architecture is human-machine teaming.
This is where it all comes together. It's about recognizing that the relationship between humans and AI isn't one size fits all.
It's a partnership.
Exactly. And it depends on the task. You have things like spam filtering, where the machine is mostly in charge, but with human oversight. And then you have complex things like business mergers, where humans are leading and AI is providing support.
Okay, so we've got a good overview of the whole AI system. Now let's zoom in on machine learning itself.
Back to the core.
What exactly is machine learning? The MIT expert defined it as algorithms that can improve their performance based on experience.
And that experience comes from data.
Right. So computers are essentially learning to program themselves based on the data they're given.
That's the key idea. It brings together techniques from statistics and computer science to allow systems to learn and adapt without explicit instructions for every situation.
And they had a nice way of contrasting traditional programming with machine learning.
Yeah, it's a good way to see the difference.
In traditional programming, you give the computer data and a program, a set of instructions, and it gives you an output. With machine learning, you give it data and the desired output, and the system figures out what the program, the instructions should be to get that output.
So it's learning by example.
Exactly. And then within machine learning, there are those 3 main approaches. supervised learning, unsupervised learning, and reinforcement learning.
The three main flavors.
Let's start with supervised learning.
Okay, in supervised learning, you're working with data that has labels. You have inputs paired with the correct outputs, like a picture of a cat labeled cat. And the goal is to train a model that can then correctly predict the output for new data it hasn't seen before.
So you're teaching it by example and then testing it to see if it learned.
Exactly. And the two main types of problems you tackle with supervised learning are regression, where you're predicting a continuous value like the price of a house, and classification, where you're predicting a category like whether an email is spam or not.
And you usually split the data into a training set to build the model and a test set to see how well it performs.
Yeah, you train the model using the labeled data and then test it on data it hasn't seen before to see how well it generalizes. Building the model is called training, and using it to make predictions is called inference.
Okay, next up is unsupervised learning.
All right, so with unsupervised learning, things are a bit different. You're working with data that doesn't have any labels. The goal isn't to predict something specific, but rather to find hidden structures or patterns in the data itself.
So it's more about discovery.
It is. Like, you might give the system a bunch of pictures without any labels, and it tries to figure out which ones are similar to each other. Common tasks include clustering, where you group similar data points together, and dimensionality reduction, where you try to simplify the data without losing too much information.
So instead of telling it this is a cat, you're saying figure out what's going on in this data.
Exactly. And it's really useful for exploring large data sets where you might not even know what you're looking for. Like in cybersecurity, you might use it to detect unusual activity without having specific examples of attacks labeled beforehand. Measuring performance can be trickier since you don't have those labels, so you might look at how well the clusters are separated or how much the data has been simplified.
And there are specific techniques for unsupervised learning.
Yeah, things like k-means clustering, PCA for dimensionality reduction, and autoencoders for creating compressed representations of the data.
And finally, we have reinforcement learning.
This one's kind of its own beast.
It sounds different.
It is. Instead of being given labeled data, an agent learns by interacting with an environment and getting rewards or penalties based on its actions.
So it's learning by trial and error.
Exactly. And the feedback is often delayed, and what the agent does can actually change the data it sees in the future.
Like a robot learning to do a backflip.
Yeah, that's a good example. You don't tell it exactly how to move, but you reward it when it gets closer to landing the flip and penalize it when it crashes. It's great for situations where it's hard to define the right steps ahead of time.
Okay, so that's reinforcement learning. And now we can't talk about machine learning without talking about neural networks.
They're definitely a big part of the conversation.
So what are they?
They're computing systems inspired by how our brains work. They're made up of these interconnected processing units called neurons, organized in layers. They learn by going through examples over and over again, adjusting their internal connections to get better at a task.
And they can be used for both supervised and unsupervised learning.
Yeah, depending on how you train them.
What makes a neural network deep? Is it just having a lot of layers?
Pretty much. There's no hard rule, but generally a deep neural network has more than just a few layers. Someone in the MIT lecture even suggested that if the network has connections that loop back on themselves, that can also contribute to depth. The point is, they have enough layers to learn really complex patterns.
And why are there so many different kinds of neural networks like CNNs and RNNs?
Different architectures are better suited for different types of data. Convolutional neural networks, or CNNs, are really good at processing images. Recurrent neural networks, or RNNs, are good for sequential data like text or time series. The availability of easy-to-use software tools has definitely contributed to their popularity.
So how does a neural network actually work? What's this forward pass thing they mention?
At a basic level, each neuron takes input from the neurons in the layer before it. Those inputs are multiplied by weights, which determine the strength of the connection, and then a bias is added. This value is then passed through an activation function, which introduces nonlinearity, and that produces the output of that neuron. This output then becomes the input for the next layer, and so on. That's the forward pass, moving the input through the network to get an output.
They even gave a numerical example of a single neuron. doing this calculation. It seemed like a fairly simple calculation repeated a lot.
It is. The complexity comes from the sheer number of neurons and connections. Training the network is all about finding the right values for those weights and biases, and that takes a ton of data and computing power. There are techniques like splitting the data or even the model itself across multiple processors to speed things up.
And they talked about how the nonlinearity in the activation functions is what gives neural networks their power.
Absolutely. It lets them learn complex decision boundaries that simpler methods can't.
There's also a lot of decision-making involved in designing a neural network, like how many layers to have, what type of network to use, how to train it, and so on.
Right. But the good news is there are things like transfer learning, where you can start with a pre-trained network, which can save you a lot of work. And how you prepare the input data, called feature engineering, and combining different types of data can also make a big difference.
Okay, let's shift gears and talk about something that's been getting a lot of buzz lately, generative AI.
This is where things get really interesting.
Our Google Cloud tech source described it as a type of deep learning that can create new content, not just classify or predict things.
Right. So instead of looking at a picture and saying, that's a cat, a generative AI could learn what cats look like and then create a completely new picture of a cat that has never existed before.
That's amazing.
It is. And they pointed out a key difference: the type of output. If the output is a number, a category, or a probability, it's likely a discriminative model. But if it produces things like natural language, images, or audio, it's probably generative AI.
So it's about creating things, not just recognizing them.
Exactly. And the process is more involved. They talked about using code, labeled data, and unlabeled data to build these powerful foundation models that can be adapted for various tasks.
So it's like a leap forward from traditional programming, which was all about rules, to neural networks that learn from examples, and now to generative AI that can create.
It's a progression, and large language models like PaLM and LambDA are good examples. They've been trained on huge amounts of text and can do things like answer questions and generate text that sounds like a human wrote it.
It's mind-blowing how far things have come. So to put it formally, generative AI is AI that creates new content by learning from existing content through training, creating a statistical model that can be used with prompts to generate new outputs.
That's a good definition. And those large language models, for example, are essentially predicting what the next word in a sequence should be. They're incredibly good at recognizing and continuing patterns in language, and something called transformers has been a major breakthrough in natural language processing.
And that brings us to prompts.
Yeah, a prompt is basically a piece of text that you give to a large language model to guide its output. And prompt design is the art of creating those prompts effectively to get what you're looking for.
Because it's all about how the AI interprets that prompt.
Exactly. They also talked about different types of generative AI models based on what goes in and what comes out. Text-to-text for things like translation, text-to-image using diffusion models, and even text-to-video, text-to-3D, and text-to-task models that can answer questions or take actions.
The possibilities seem endless.
They really do.
Yeah.
And these foundation models are powerful because they can be adapted for so many different tasks. Like Google demonstrated how Bard can be used to generate code, debug it, explain it, create database queries, translate it, and even write documentation.
They also talked about Google Cloud's Generative AI Studio, which lets you explore and customize these models, and the Generative AI App Builder, which lets you create apps without coding, as well as the PaLM API for experimenting with these models.
It's becoming more accessible.
Okay, we got a good grasp on AI and ML, how they work, and how they're developing, including generative AI. But how are they actually showing up in our everyday lives?
Well, our fundamentals guide gave some really concrete examples, and what's interesting is how often we interact with AI without even realizing it.
It's become part of the fabric of our lives.
It has. Like the algorithms that decide what we see on social media recommend products when we're shopping online, or power those chatbots that answer our questions on websites. Even voice assistants rely on AI to understand us and respond.
AI is also making a big impact in healthcare.
Definitely. It's being used to analyze treatment effectiveness, help with diagnoses, speed up drug development, personalize medications, monitor patients, and even assist surgeons during robotic surgery. The rise of connected medical devices combined with AI is also helping people manage their own health.
It's not just healthcare, though. AI is transforming agriculture, too.
Absolutely. From predicting crop yields and detecting pests to automating farm equipment and monitoring soil health, AI is being used in many ways. They even talked about a Microsoft AI sowing app that uses AI to advise farmers on when to plant their crops, all through simple text messages.
That's pretty cool.
It is. And AI is also revolutionizing retail.
How so?
It's helping with everything from supply chain management and demand forecasting to personalized recommendations and sales predictions. By analyzing customer data, AI can help retailers optimize inventory, understand purchasing behavior, and ultimately improve customer satisfaction.
And AI is even boosting productivity in the workplace.
Definitely. It's being used for things like analyzing job descriptions and candidate qualifications to help with hiring. It can also help with scheduling meetings, writing emails, and even checking grammar and spelling.
Even the guide we're looking at was probably created with the help of AI.
Most likely.
The guide also went into detail about specific AI applications, like natural language generation, or NLG.
Yeah, NLG is used to turn data into human-readable text. It can summarize financial data, generate responses for chatbots, and even filter spam.
And then there are virtual agents and conversational AI.
Virtual agents are getting more and more sophisticated, able to handle complex customer service and IT support questions. And conversational AI, like chatbots and voice assistants, is automating communication and creating personalized experiences for customers at scale.
And underpinning a lot of that is natural language processing, or NLP.
That's the tech that allows computers to understand and process human language, enabling things like text summarization, translation, and sentiment analysis, which is figuring out the emotion behind text.
They also mentioned natural language understanding, or NLU, which is about extracting meaning and intent from language.
Right. It's a key part of making these systems work.
And they touched on biometrics for identification and robotic process automation, or RPA, for automating repetitive tasks. It seems like AI is everywhere.
It really is. And to make these capabilities more widely available, there are APIs, which are like pre-built AI tools that developers can use without being AI experts themselves.
Like plug-and-play AI.
Exactly. And then they talked about public databases, which are open sources of data that can be used to train ML models, but they cautioned about data quality and potential privacy issues.
Always important to think about the source of the data.
Absolutely.
Okay, we've looked at the present and the past of AI. What about the future?
Well, for that, we turn to Mustafa Suleiman's TED Talk. He's been in the field for a long time and has some really interesting thoughts.
And he's seen it all firsthand.
He has. And he starts by pointing out how quickly AI has gone from a niche research area to outperforming humans in tasks we thought were unique to us, like understanding images, translating languages, and even diagnosing diseases.
It's been a rapid rise.
It has. And he shared a story about his nephew asking him, "What is an AI anyway?" which led him to suggest that we should think of AI as a new kind of digital species.
A digital species.
Yeah, it's an analogy, not a literal description, but it's a thought-provoking way to think about it. And he goes on to list what AI can already do. Communicate, see, consume information, remember, even have a sort of personality, be creative, and do some basic reasoning and planning.
It's a pretty impressive list.
It is. But he also draws a comparison to human history, pointing out that while our technological progress has been great, it's also had some downsides. He suggests that we have a chance to do better with AI, to develop this digital species more responsibly.
To learn from our mistakes.
Exactly. He also talks about data and computer chips being the new oil, and this idea of autonomous AI that can update its own code and explore without direct human oversight. He thinks this is still some years away, but it's something we need to start thinking about now.
It's like opening a whole new chapter.
It is, and he points out a key difference between biological and digital species: replication speed. Digital things can copy themselves almost instantly.
That's a big difference.
It is, and it raises the question of whether we should deliberately build self-replication into AI. He argues against it, saying it would be dangerous.
Yeah.
He believes self-replication won't just happen accidentally. Someone would have to design it that way.
So we've got this incredibly powerful technology that we need to guide carefully. Right. It's a big responsibility.
It is, and it brings us back to the importance of building robust and responsible AI.
Okay, let's sum up what we've covered. We've done a deep dive into artificial intelligence and machine learning, looking at what they are, how they've evolved, the key parts of an AI system, and how machine learning algorithms learn. We even explored how neural networks work and the possibilities of generative AI.
And we saw how AI is already woven into our daily lives, from healthcare to agriculture to how we shop and work. And we've also considered the big implications for the future.
So as we continue to build this digital species, as Suleiman put it, what are our responsibilities in shaping its development? How do we ensure a positive future for both AI and humanity?
It's a question we all need to grapple with.
We encourage you to keep exploring these ideas, maybe delve deeper into specific applications that interest you, or consider the broader societal implications with this newfound understanding. The story of AI is far from over.
It's just getting started.
And it's going to be a fascinating ride.
That's for sure.